This is Chapter 10, Technical Math with the Sharp Calculator. In 2 video lessons, I'll be explaining how to use the Sharp series scientific calculators and Microsoft Excel to do regression, and the Sharp calculator, solving linear equations, solving quadratic and cubic equations, and differentiation and integration. There's an Excel file that goes with this, and I'd like to begin there. So this Excel file is on Blackboard. It's called Calculator Lessons, and we'll be starting on the first tab, the first worksheet, called Forecasting. I want to explain how forecasting works. In analytical chemistry, we often prepare sets of standards of known concentration, and we read these standards on an instrument and obtain an instrument response. We also take readings of samples of unknown concentration, and then we can forecast the concentration of the unknowns by any of several methods. For example, plotting and interpolating a graph, or determining and solving the equation of a line, or performing regression analysis. And before the days of Excel, and before the days of handheld calculators, it was all done graphically. Let's start here to make sure we understand. Let's assume for a minute that we have 4 standards of known concentration that we've prepared, and these concentrations are 1, 2, 3, and 4 ppm. And the instrument response was 5, 7, 9, and 11 units. What we would then do is plot a graph, concentration in ppm on the x-axis, that's our independent variable, instrument response, our dependent variable, on the y-axis. And here's what our graph would look like. Now, the reason we do this is that we want to know the concentration of some unknown samples. So I have several unknowns here. If, for some strange reason, we knew the concentration of a sample, and we wanted to forecast its instrument response, we could read our graph. For example, if a concentration of a sample was 1.5 ppm, we could forecast that the instrument response would be 6 units. If our sample had a concentration of 2.5 ppm, then we could forecast an instrument response of 8. Now, more commonly, we measure the instrument response of our unknowns and forecast the concentrations. So, for example, in this sample here, unknown number 3, an instrument response of 6 was measured. What's the concentration? We read the graph and say it's 1.5 ppm. Or here, if an instrument response for unknown number 4 measured 8, we could read the graph and say the concentration of the unknown is 2.5 ppm. An alternate method is to solve the data for the equation of the line. The standard equation of a straight line is y equals mx plus b. We could use this 2-point equation of a straight line, take any 2 points, substitute the values in, rearrange, and determine that the equation of the line is equal to y is equal to 2x plus 3. Once we have the equation of the line, we could substitute any x values in and solve for y. We call them y prime because they're forecasted. We could substitute 1.5 for x and solve for y prime being 6, and so on. But more commonly, what we want to do is solve for x. So we'd have to rearrange the equation and isolate x, and then substitute values of y, our instrument response, and then forecast the values of x, the concentrations. Now, this process of using the data to obtain an equation of the line and then forecasting data from our equation of the line has been automated for us in software like Excel and in handheld calculators. And the purpose of this lesson is to learn how to use our calculator to do this. On page 532 in your course notes, I have an image of the Sharp EL520 and or 546 showing you the important keys necessary to do stats and regression analysis on this calculator. On page 233, I have the same information, this time for the Sharp Right View EL516X calculator. On page 234 I have the image and important stats keys for the Sharp Right View 516 XG calculator, which is the one I'll be demonstrating today. This is the newest and certainly the easiest of the bunch to use. On page 235 of your course notes, I have instructions for entering a data set into the linear regression mode of the Sharp EL520W or 546W calculators. When you select mode, you'll see that there are 7 different regression types available using keys 0 through 6. I have instructions for entering a data set, correcting a data set if you make a mistake, and then forecasting values from the data set. On page 236, I have the same information, this time for the EL516 or 506X calculator. On page 237, I have the same information, but this time for the ELW516XG calculator. Notice the types of regression that can be performed on this calculator. We have linear regression, quadratic regression, Euler exponential regression, logarithmic regression, base E, power regression, inverse regression, and general exponential regression. And I'll be illustrating how to do this on this calculator next. Notice that in statistics, the equation of a straight line is y is equal to a plus bx, rather than y equals b plus mx. Easy to confuse these. You'll have to be careful to keep them straight. Once you've entered a data set into the calculator, you can then forecast unknowns. I'll show you how to forecast a y value that corresponds to a given x value. I'll show you how to calculate an x value when you enter a y value. So here's the Sharp Right View ELW516XG scientific calculator. We're going to enter this data set in the linear regression mode. So select mode, and then you want to select 1, which gets you to the stat mode. In the stat mode, there are actually 8 different stats types. I'm scrolling up and down just to show them to you. But ultimately, you want to press 1, which gets you to the linear regression mode, a plus bx. There it is, 1. If there's data you want to clear, second function mode, which clears it all, then you have to press the data key to get you back to the table so you can enter your new data. Okay, our first point is 1. See it in the bottom of the screen. Then xy, comma, you see the comma, then 5, then equals or data. Second point is 2, xy, 7, equals. Very easy to use. 3, xy, 9, equals. I'm going to deliberately put in the wrong value here to show you how easy it is to correct. 4, xy, I'll put 12 instead of 11. And hit enter. Uh-oh, what do? Just scroll up, put your cursor over the wrong value, type in the correct value, and hit equals. Very simple to correct. Once all your data is in, just scroll through it to make sure it's correct. Looks good. When you're done, press the clear button. Doesn't eliminate it from the memory, it just clears the display. So now to forecast, we're going to enter an x value of 2.5, and then we'll go second function y prime. It'll give you the corresponding forecasted y value. And in the right corner, you see it's 8. Now we'll enter the y value of 8 and forecast x prime, so it's second function x prime, and it should be 2.5. We can clear that. Let's click Alpha Stat. It'll show you the regression statistics. Alpha and Stat. Blue recalls blue. So let's pick 0 to see what statistic variables are available. All kinds. We have number of points, x bar, standard deviation, variance, goes on and on. There's population standard deviation, population variance, max, min, and on and on. Lots of stats. We'll clear that and go alpha stat again. This time we'll choose number 1, regression variables. This will give you the regression coefficients of the equation of the line. A and B and R, and if you scroll down, R squared. If we clear that, alpha stat, let's check out the variables, number 2. So a list of individual variables, you select the one you want by selecting the number. I'm just going to choose number 1 for x bar here as an example. This tells me x bar equals 2.5. Great calculator, easy to use, very powerful. Well worth the $40 it costs. If you want to clear the data, recall, just go to the data table, second function, mode, which is clear all. And that's it. On page 237, the data that you entered into the calculator had a perfect fit to the regression line. The R squared was 1, but it's highly improbable, if not impossible, to perfectly fit real data because real measurements have scatter. So if you go to page 238, please. On page 238, I want you to replace the second y value from 7, please make it a 6, and then reevaluate the regression coefficients. You'll find that the intercept has changed from 3 to 2.5, and the slope has changed from 2 to 2.1, and the R squared has changed from 1 to 0.9692. So this is now imperfect data, which is more realistic in a sense. Then I'd like you to forecast all of the x prime values for the measured y values and calculate and compare x prime minus x, the difference from the measured value for each point. Do the same, forecast the y prime values from all the measured x values and calculate and compare y prime minus y for each point. So you do this in Excel and you'll have a table to fill out like this, and I'll walk you through the first example and I'll show you it. So for example, if you entered the value, the measured value of y as 5, and then second function x prime, you'll forecast the value of x from the regression line, and it's 1.19 instead of 1. Then calculate the difference between the forecast and the measured value. That'll be 1.19 minus 1 is 0.19. Then I calculate the percentage difference between the forecasted value and the measured value. So here's the difference divided by the measured value times 100 gives you 19%. I'd like you to do that in Excel. I'll show you the sheet. So here on the tab marked y equals 2x plus 3 in the top left corner, I filled in the first data set for you, but I'd like you to go ahead and fill in the values of slope, intercept, R squared that you get from the calculator, and forecast all your x prime values and calculate the differences and percentage differences. Same for the y prime values. Now I've got a short video clip to show you how to do that. All right, the data has been entered. Press the data key to see the data. There it is. Let's check it. 152639 right? Now 26 is the bad point. We changed it from 27 to 26. That should ruin our R squared. Clear the data. Go to alpha stat. Let's check the regression statistics. Number 1, regression variable. So there's A, the intercept. You can write that in under intercept. B is a slope. And if you press the down arrow, we'll see the R squared. So enter that on the Excel spreadsheet in that spot. You can clear that. And now we want to forecast. So enter a value of 5 for y, press section function x prime, because we want to forecast an x value. The value is 1.19 instead of 1. So write it on your table in Excel. Now we want the difference between the forecasted and the measured value. So subtract from it 1, which was the measured value. The difference is 0.19. Now we want the percentage difference, so simply divide that difference by the measured value of 1, multiply by 100, and it's 19%. Go ahead and complete the table on the left and do all the values on the right for x and y, and then compare to the spreadsheet. So by now you've completed this table, entering the data from your calculator. Now your values may not be exactly as mine are, depending how many decimal points you carried or used, but it should be very similar. Now what's this telling us? Let's plot the data in Excel and take a look at a graph. So select these 4 points, measured values, choose Insert, and then choose Scatter Plot. Now choose a scatter plot with no lines connecting, just markers. Say OK. I'm going to move this out of the way. All right, so with the chart still selected, in the Design tab, if you slide over to Quick Layout, click on Quick Layout. Let's choose Layout number 1. It provides placeholders for axis titles. It's an easy way. To relabel the x-axis, click once on the axis title label. Click a second time. When you see the flashing cursor, you can hit Control-A, which means select it all, and type in what you want. In this case, we'll just call it X. Do the same for the Y values. Select it, click a second time till you see the cursor, Control-A selects it, type in Y. What do we call this chart? Let's call it Sharp Lin Reg, Linear Regression. We don't need this legend because there's only one data set. All right, so now right-click on any one of the points and choose Add a Trend Line. Now by default, a linear trend line is chosen. Let's go ahead and display the equation of the line and display the r-squared value. Now I'm going to close this box. Anytime you display an r-squared value, always show 4 decimal places. 5 is not really meaningful. Always show 4. If it isn't 4, simply right-click on the label, it's called a label, and go Format Trend Line Label. In this Categories, Numbers box, choose Number and specify 4 decimals. And say OK. Now it gives us a lot of decimals in the coefficients, which are more than we need, but we do need 4 decimal places in the r-squared for evaluating it. So what's this chart telling us? Well, certainly it easily identifies one point as being a flyer or outlier, but we don't have this visual on the calculator. Let's go back to our data and understand this. Let's go back to your notes. This is on page 238. Here's our plot. So the trend line or regression line added to the chart shows one flyer or outlier that biases the regression line. It pulls it down or below all the other points because remember the y value was too low. And this clearly indicates that one point is biasing the results. So when you see this, this sample should be checked, measured again, redo the calculation, make up another dilution, do it right away if you can. If you can't retest the sample, this data point likely should be discarded. Now, what about the table? What was the point of that? Well, if you look at the percentage differences of the y prime compared to y values, you'll notice that the first y value was 8% low. Regression line, that's y prime minus y. See, the regression line is pulled low, so it makes sense it's negative. And the third and the fourth point are also, the regression line is below the actual measured value. So we get negative differences in those cases. But for the second point, the regression line sits above this second point, and so y prime is greater than y, and therefore we get a positive difference. When you see this change in sign, it indicates which point is biasing the regression line. If all your points are randomly varying, and they should be, you'll get a collection of positive and negative values, so that's not necessarily a good indicator. This is true when you have one point in particular that's way off. However, look at the magnitudes. The magnitude of the difference is greatest for this second point. That's a good indication that this point is the worst point. If you look at the percent differences on the x values, we see a similar kind of pattern. 3 of them are positive, but 1's negative. That's an indication that this point may be off. I would just caution you about considering percent differences. Percent difference is a good indicator. It's a very good indicator. But when you're doing a percentage difference from a value that's near the origin, from a low value, then a small absolute difference is exaggerated as a percentage. So be careful about how you interpret a percentage difference on the lowest value. So an Excel chart with a trend line and a residual plot, which I'll show you later, are tools that quickly identify bad points. However, if you cannot plot your data in Excel immediately, as readings are being taken in the lab, then a handheld calculator with regression capability, it really should be used to plot your data in real time as soon as you get it, and evaluate your data as soon as it's measured. It's much easier to correct a bad point, to retest the sample while the analysis is being performed, rather than after you've completed it and go to the computer. You can't access your samples, you can't repeat a sample. All you can do is decide, do I keep or discard the bad point? Back in our Excel spreadsheet, we've calculated the percent differences based on calculator data, but now I'd like you to repeat that entirely in Excel. Let me show you how it's done. So we'll need to calculate the equation of the line, y equals intercept plus slope times x, and we can substitute values of x in and calculate y prime. We can also rearrange the equation for x and substitute values of y in and calculate x prime. To get the equation of the line in this cell, we could type the coefficients of the equation by copying them from the regression plot. But that's tedious. Furthermore, it's prone to making mistakes. There's a couple of functions in Excel you should be familiar with. There's one for slope, one for intercept, one for r squared. So for slope, you could start by typing it in like before, but I want to show you another method here. It's in the insert function group. So try typing the name slope up here, and there it is, say slope. So just say OK, and just follow the prompts. So the known y's are the y values that were measured. The known values are not the forecasted y values. They're the ones that you measured. The known x's are the known values of x, the standards that you prepared. And just say OK. So there's our slope. There's likewise a function for intercept. Insert a function. If you type in intercept, there it is, say OK. Again, follow the prompts. The known y's are the measured y's. The known x's are the standard concentrations, and say OK. There's also a function for the r squared. It's called RSQ, r squared. OK. Known y's, known x's, and OK. Those are the same values you got in your calculator. So now we can calculate our y primes using the equation of the line. Y prime is equal to the intercept plus the slope times x. That'll be equal to the intercept. Now we're going to want to drag this formula down. We need an absolute reference to this cell, so press F4, plus the slope, which is here on cell C30, F4 for absolute reference, times the value of x, which is in cell E23. Say enter. and you can drag that value down. And those should be the same values you got from the calculator. I'll just scroll up, and yes, those are the same. Now for the difference, it'll be equal to the forecasted value of y minus the measured value of y. Enter. These are relative references, so I can drag the formula. And for the percent difference, it'll be equal to the difference divided by the measured value times 100%. Notice we got an error message here because we are dividing by a value that's 0, and that's not possible. So this was one of our unknowns, so we didn't have a known value of y, so we can discard that. Likewise for the x's, we'll have to rearrange our formula. X is equal to y minus the intercept divided by the slope. So in the cell I'll type equals bracket. Now y is this value here, 5, minus our intercept, f4, close bracket, divided by slope, f4, enter. 1.19 looks correct. All right, before I drag that down, let's do the rest of these, and we'll drag them all down at the same time. This is equal to the forecasted x minus the measured value or known value of x. And this percent difference will be equal to the difference divided by the true value times 100. Enter. 19. We can select all of these and drag them down simultaneously. You can drag this one down too and see what we get. This point has no meaning, but otherwise it looks good. So it's the same as done by the calculator, except certainly more handily done in Excel. On page 239, there's an exercise for you to do regression on some non-linear data. This data happens to be semi-logarithmic. And there are 3 cases here. And the answers are on page 240. So you can do this on your calculator and check the answers on page 240, but let me explain it on the spreadsheet. So this is the same data. What we have here is the concentration of ammonia reported as ppm nitrogen, 0.1, 1, 10, and 100 ppm. And this is an instrument response to that. Now the instrument we're using is called an ion selective electrodes, ISE. So an ISE instrument is the same as a pH meter, except it has a different electrode. See, there are many different electrodes that can be used in a specific ion meter. pH is one of many. This particular one we're using here is an ammonia electrode. Actually not ammonium, but ammonia. But ammonium can be converted to ammonia by adding base, and that's how it's used. Here's the equation that describes the relationship between concentration and millivolts. You see the log of the concentration is proportional to the millivolt reading, or the output of the instrument. The instrument's output is in millivolts. So let's just go ahead and plot this data and take a look at it so you see that it's not linear. Select the x values, hold down the control key to select a non-adjoining group of cells, scroll over the next cells. They're both groups of cells are selected. Go to Insert, a scatter plot. Let's choose one with curved lines just so we can see it. That is clearly not linear. And so we can't use linear regression directly on the data. It would be bad news. It wouldn't be linear at all. If I right-click on one of these points and add a trend line, and I say linear, display the equation of the line, it's terrible. The r-squared is only 0.7. It should be 0.99 something. Here's the best attempt at a linear fit. So clearly this data is not linear. We don't want to use linear regression on the data as is. But we can make the data linear since we know the relationship the log of the concentration is linearly related to the millivolt reading. So why don't we do that? So let's get the log of these values. The log of 0.1 is -1. The log of 1 is 0. That's log base 10, right? The log of 10 is 1, and the log of 100 is 2. Now if we enter this data, this should be linear. Let's insert a scatter plot. We'll use curved lines. Much more linear, right? We can right-click on one of the points and add a trend line. And linear, let's see. This looks a lot better, right? 0.9989. So we can linearize the semi-log data by taking the common log values of the concentration values. And that's what we'll do. So you can now enter the log of the concentration versus the millivolt readings into the linear regression mode of your calculator. And when you do that, then you can forecast log x prime, then take the anti-log of this, 10 to the log x prime, and calculate x prime and compare those to your concentrations. Then you can forecast your unknown samples. I'll show you how to do that in a short video. Alright, so we want to enter this data set log x and y. Choose mode, 1 for stat and 1 for linear regression. Enter the data pairs. Now I've sped this up because you've seen this a few times now. It's just x value, xy, y value, and data, or enter. Once you have it in, good idea to scroll through and check that it looks correct. Then you can clear the display, get the regression stats, choose alpha stat, and 1 gives us the regression coefficients. There's A and B, and scroll down for R squared. You can clear that. Now let's forecast. Enter 95.6. That's our y value. Second function, x prime, gives us the corresponding x value. But that's log x. We want the anti-log. So type second function log equals, which is 10 to the x. And we'll get the anti-log, which is the actual ammonia concentration as nitrogen. Alright, so I presume that you've worked out all these values from your calculator. Did you remember to forecast the unknown concentrations from the unknown samples? That's the only reason we do this. We want to calculate the concentration of unknowns, so we run a set of standards, and then at the same time we run our unknowns and forecast. Now then you wonder, well, why do I bother to forecast the standards? Why don't I just forecast the unknowns? Well, how do you know if your unknowns are good or not unless you forecast your standards? If your standards are good, it's quite possible that your unknowns are good. If your standards are bad, it's pretty much a certainty that your samples will be bad. Well, how do we know? We look at the R squared. Well, what's that tell us? 0.9989, it says it's so-so. It's not great. It's not 4 nines. So look at the actual data. Here the known concentration of the standard was 0.1 ppm. What did we forecast? 0.102. Is that good or bad? Well, let's change it to a percentage. Move the decimal over 3 places. This would be 100, and this is 102. So we're 2% high. Is that good or bad? On an ion selective electrode, that's what they're rated to perform at, about plus or minus 2% if calibrated every 20 minutes to half an hour. So that's okay. But the next result, we had 1 ppm standard, we measured 104. So move the decimal over 2 places, that's plus 4 parts in 100, plus 4%. That's getting kind of high. That's not that great. Check out the 10 ppm standard. You measured 8.7. Ooh, that is terrible. If this was 100 ppm, this would be 87 ppm. You are 13% too low. That's terrible. And that's the reason why you should run regression while you're getting your samples, so you know right away. If you took your data home and looked at this, you have no option but to discard the data. And then you're down to 3 data points maximum, and that's not good. But if you'd run it right at the time you did it, You could have caught the fact that your partner spazzed here, and you could have made a new standard or run it again and checked. On the 100 ppm standard, we're measuring 108, still not great, that's 8% too high. The reason you forecast your knowns is that you know how to evaluate your unknowns. So what about these unknowns? 0.43 ppm, do you think that's close? It's probably not too bad since it's between 0.1 and 1, and we're in this range. We were anywhere between 2 and 3% error, so it's probably acceptable. But the values that are around 5 and 35, they're in a very bad zone here. Probably this data is of no use other than to give you a rough idea. You really need to go back and run it again. Let's do the same calculations, but now we'll use Excel. So we need the log of the concentration values equals log. There's no difference between log and log 10. It's the same thing. Tab of the concentration. M18, close bracket, enter. I can drag this formula down because I use relative referencing. Now I need to forecast the log x values. How do I do that? Well, I need a formula, right? If I have the slope and intercept, I can get one. Let's get that from Excel. Remember how? You can use the insert function tool here. I'm in the recently used group, so they should be here because I just used them recently. I want the slope. There it is. Okay. The known y's and the known x's. Now make sure you put the log of x's. We're plotting log x versus y. That's what's linear. X versus y is not linear. And then say OK. Minus 5730 looks the same. Okay, how about the intercept? Insert a function, intercept, OK. Known y's are here. Again, we want the known log x's here. And say OK. 38.8, same number. Now we want, let's get the RSQ. R squared, known y's, and known x's. That is known log x's. Okay, same values. All right, so now we can forecast log x prime by rearranging our regression equation. Log x prime is equal to bracket y minus the intercept here. Make sure you hit F4, absolute reference, close the brackets, divided by the slope, which is here, and F4 again, and enter. Same value as above. Now we need x prime. That'll be the anti-log of the log, so that's equal to 10 raised to the power of the log. Enter. Same value. Let's select them all, drag all the way down. Same values. Very easy in Excel to do, right? Now there's another way we could perform regression on this semi-log data. Instead of using the common log or base 10 log, we could use the Naperian log or natural log. Take a look at your notes. I'm asking you to get the ln of x instead of log of x, and do the same procedure. The answers are on the next page, and you can do it in Excel the same way. So as you get your data from the calculator, you can enter it right into the spreadsheet. Back on the same spreadsheet, just scroll towards the middle of the spreadsheet. Here on the left is the data log x. Here towards the center is the data for ln of x, ln concentration. So you can enter it in here. And I have a short video clip that follows that shows you how to do this on the calculator. So you want to enter the ln of the concentration versus millivolts. You're going to choose mode, 1 for stat and 1 again for linear. Enter your 4 data points. I've sped this up. There'll be an x value, then the xy key, then a y value, then the equals key. After you get your data points in, it's a good idea to scroll through the values and make sure that they are correct. Clear the display. Alpha stat, 1 shows you regression coefficients. Scroll down for the R-squared. You can clear that, and then regression will enter the y value 95.6. Second function, x prime, gives us the ln of x. We want the anti-ln, so we're going to hit second function ln, which is e to the x, and that'll be the concentration. 0.102 is your forecast. So here are the values that you should have got, entering ln of x versus y in the linear regression mode of the calculator. The results would be essentially the same as you'd get using log of x. Let's do it now on the computer instead of in the calculator. So we need the ln of x equals ln, that's the natural log or Napierian log, tab of x, close bracket, enter. We can drag that formula down. Right, now let's get the slope, intercept, and RSQ. Remember how to do that? Insert the slope, okay, known y's. We want to enter the known ln of x's, not the x's. That's not linear. Looks the same, right? Intercept. Known y's. Known ln x's. Okay. And I trust the RSQ will be the same. Looks good. Okay, let's forecast our ln x values. So we write an equation, rearrange it for x. We'll say the ln of x is y minus the intercept divided by the slope. Equals, bracket, the y value minus the intercept, absolute reference f4, close bracket, divided by the slope, f4, absolute reference, equals negative 2.28. Looks good. We can drag this down for samples and standards. And what about the x values? We need the anti-ln. How do we do that in Excel? We use equals exp. It gives the e to the power of whatever we enter. We want the power or the exponent to be the ln of x prime, and enter. And these should be the same as we got up here. All right, so I think we've exhausted the possibilities using linear regression. Take a look at the notes. Bottom of page 239, I'm asking you now to enter the same data set without taking the log or the ln, but rather enter the data as it is, but enter it into the logarithmic regression mode of your calculator. That way you don't have to linearize the data before you enter it. In Excel, you can enter that data to the far right side of this worksheet that you're on, the logarithmic worksheet. So just enter x and y on the calculator and go ahead and forecast the values directly. Make sure you are in the logarithmic regression mode. I have a short video that shows you how to do this. So enter the concentration directly with millivolts. Choose mode, 1 for stat. This time choose 4 for logarithmic regression mode. I wish I could work this fast. So x and y go directly in the calculator. No need to linearize the data. Looks like it's okay. We'll clear that. Choose alpha and stat to get the regression coefficients. A is the intercept, B is the slope. Scroll down for the r squared and clear the screen. Let's do regression. Enter y, 95.6, and second function x prime. Get the forecasted x value. 0.102 is the concentration directly obtained. Very nice. So here are the results you should have gotten from your calculator entering the concentration of x versus y directly into the logarithmic regression mode of your calculator. If you look at the slope and intercept, it tells you that the calculator uses the Naperian log rather than the common log in the logarithmic regression mode. Sometimes students will notice a small difference between values forecasted from the calculator versus what's forecasted from the computer. And they'll ask me, why is it different? Well, it could be that the calculator and the computer use slightly different algorithms to do the calculations. But you'll only see a difference when the r squared is rather poor, like in this case. And the differences are typically in the range of, for example, 0.3%, where at the same time, the forecast itself might be out 5 or 10%. So the slight deviation from method of regression of 0.3% is really insignificant considering the large error resulting from a poor RSQ. When the RSQ is very high, like 4 nines, you'll never see a recognizable difference between the methods. So you needn't worry that any difference is significant in your precision in your calculations. If your RSQ is good, they'll be so close you won't know the difference. If your RSQ is bad, you'll see a difference, but it's insignificant compared to the error just because of the bad RSQ. And I think we'll call this lesson a quit for today. In the next lesson, we'll carry on with showing you how to carry out regression on inverse and quadratic and power and exponential functions. Thanks for watching.